So after the plane wave in one dimension, we consider the next case of non-conducting medium. So here, assuming there is no source, like almost like in free space, and so these are the Maxwell's equations takes this form. And so if we start from here and we use Fourier transform, so there's a spatial ext, E is the electric field function of space and time, and it gives you a Fourier conjugate of Ex of omega, and they're related by a Fourier transform. Now with that you can essentially again replace in the existing Maxwell's equation and again do those substitution, and finally kind of come up with the different forms of wave equation, both for E as well as for the B. So both for electric field and magnetic field you can come up with two different forms of wave equation. And there are certain this thing, the refractive index is kind of defined in terms of this ratio of mu and epsilon, and that's how they are defined in over the free space permittivity and dielectric constant. You know that the c, the speed of light, is 1 over square root of epsilon 0 mu 0, and the phase velocity is defined by omega over k, so that is c over the refractive index. Continuing further, you finally get the solution, the harmonic solution of both the electric field and magnetic field, and you have the k vector as the wave vector, which k is the amplitude is 2 pi over lambda, and n is the direction of propagation. So ultimately you will, if you proceed further in this calculation, it is very cumbersome, but I mean, finally we get that proof that E and B fields are actually perpendicular to each other, and that's their direction of propagation. So these are two fields which are orthogonal to each other, and that's how electromagnetic waves propagate. And we also can define plane waves, this impedance of free space, and that is defined as Z0, which is the ratio of epsilon 0 over mu naught, and that is roughly 377 ohms. If you define E and H, if you finally solve for E and H, then you can also derive what is the Poynting vector, and from there you can derive the average energy density U. Okay, that's how it's related. Now that was in the non-conducting medium. Of course, if this real media is lossless, lossy, and so here we consider lossless media, and again the different wave equations takes place. We define a propagation constant, which is complex, which has alpha and beta. Beta is the complex term and alpha is the real term. So if you solve for the waves equation, you can actually derive the value of alpha and beta. The third and the last example, we did non-conducting medium, free space, non-conducting medium, and then lossless medium, and finally the real world is lossy. So if you do that, the alpha beta values becomes quite extensive, and quite cumbersome. But that's how things are done. We just show you there is nothing to worry about, that we will never be using this for this particular course at least. But that's how you're done. Okay. So that brings us to the end of the second topic of the electromagnetic waves. So the third topic is the polarization of electromagnetic waves. As you know, as we learned, that electric and magnetic fields are always propagating but orthogonal to each other. That gives rise to something called polarization, and different polarization, linear polarization, circular polarization, and elliptical polarization. And under circular there is left-handed circular polarization, or LHCP, or commonly called left circular polarization, and right circular polarization. And then again similar, that is RHEP, right-handed elliptical polarization, and left-handed elliptical polarization. So let's consider the X is a linearly polarized wave with complex amplitude of Ex, and Y, along Y there is a linearly polarized wave with complex amplitude of Ey. But they both travel in the positive Z direction. So note that Ex and Ey may be varying with time. That's a general case. The complex, for simplicity, we ignore the time varying part and just concentrate on the spatial term for a little bit. So E vector is composed of both Ex, which is along X, and Ey along Y, and they are also substituted further, and so we can consider the equation this. And so if you have the, so both Ex0, Ex has a component of Ex0 times e to the power j phi of X, and Ey has j phi of Y. Now if the two linear polarization, the time phase difference with the two components is either 0 or integer multiple of pi, then this is called the linear polarization. Okay, and if they are not n pi, but the amplitude of Ex0 and Ey0 are same, but the phase difference is either plus of 2n plus half pi or minus 2n plus half pi, then they are called circular polarization. Then there is left circular and right circular, and that is linked here. And if the Ex0 and Ey0, the amplitudes, are not equal, then as well as the phi phase difference is like this, goes from either plus 2n plus half pi or minus 2n plus half pi, then these are basically called the elliptical polarization. Okay, CW stands for left-handed circular polarization, and CCW is counterclockwise or right-handed circular polarization. Similarly, for the circular polarization also, there is left-handed and right-handed properties. We will come to all of this when we learn about antenna radiation and stuff. Another way of looking into polarization is by measuring Stokes parameters. Following Stokes 1852, the definition of 4 Stokes parameter. I is the quadrature sum of both the amplitudes, E1 square plus E2 square. Q is the difference of that. U is the cross product, 2 E1 E2 times cosine of delta, and V is the other cross product, 2 E1 E2 sine delta, where delta is representative of the phase difference, which we just concluded in the previous slide. And angular polarization is given by half of tan inverse U over Q term. So this is very standard way of understanding the different types of polarization by quantifying the I, Q, U, V Stokes parameters. For radio astronomy also you will see that the Stokes I is basically the ignorant of the polarization, but the V is the differential. And so we will see the Stokes I image, Stokes V image, and so on and so forth when we do imaging of the radio data. Beside this, there is another way of by following Henry Poincaré to essentially represent the state of polarizations in a sphere. So if the polarization is lying near the equator, the vector, it basically means linearly polarized. If they're lying in the north pole, it's left circular, and in the south pole, it is right circular polarization. There are more details to it. We will deal with it later, but it's a very nice way to visually represent the state of polarization of a electromagnetic wave. So thanks a lot. I mean, this probably has come to you a little bit intense. We will also follow this up with a kind of a easy tutorial which will explain this stuff and make it more easier to understand. But nevertheless, we will, for people who are registered for the exams, don't worry much about it. It is just for completeness and thorough understanding of the subjects which are going to come up. We thought better to introduce all this in the first week itself. You can go and just do a revision of your basic electromagnetics from Griffiths or any other book which you like, and we hope this will help. We will also take up individual concepts again as a part of that week's lecture, and we again revisit those when time comes. So don't worry, stay tuned for the next week's lecture. We start with brightness, temperature, different radiation fundamentals. It will be fun. So see you soon. Bye.